Now in the previous lecture we have learned what is dynamic programming and properties of dynamic programming. In this lecture we will learn different methods of dynamic programming for solving problems. Now the first approach is top-down with memoization. In this approach we try to solve the bigger problem by recursively finding the solution to the smaller subproblems. Whenever we solve a subproblem, we cache its results so that we don't end up solving it repeatedly if it is called multiple times. Instead, we can just return the saved result. This technique of storing of results of already solved subproblems is called memoization. Basically, what we are doing over here is, here we are dividing the problem into subproblems and then we solve these subproblems. And solutions to these subproblems are stored to be used for future cases where we face the same subproblem. So here, the main idea is we start from the top, which is the main problem, then continue to the down by dividing the main problem into subproblems. Then while we are solving the subproblems, we are saving the result of these subproblems, because if we face the same subproblem, we are not solving it multiple times, we are just using the result that we got before. Now to make this very clear, let's see the Fibonacci example that we explained in the divide and conquer section. So we know that in a Fibonacci series, the current number is obtained by adding the previous two numbers, and the first two numbers are always 0 and 1. Now this is the equation for Fibonacci, so you see that n is equal to n-1 plus n-2. Now in the case of divide and conquer algorithm, we have used this algorithm to find Fibonacci series of any given number. Now in case of divide and conquer algorithm, we have used this algorithm to find Fibonacci series of any given number. Now here you see that we are having two recursive calls, and because of this the time complexity is exponential time complexity. So here we see that it's a very time consuming process. Now we know that if we have exponential time complexity, it means that this is not very time efficient, so it's very problematic solution. So we need to find out the problem over here. Now to understand the problem, let's look at the recursive tree of this algorithm over here. Now the recursive tree will look like this. So here we see that if we want to find the sixth number of Fibonacci series, we need to calculate the Fibonacci series of 5 and Fibonacci series of 4. And then to find the Fibonacci series of 5, we need to calculate Fibonacci series of 4 and Fibonacci series of 3. So it continues like this until we reach the Fibonacci series of 1 and 2. Now this is normal recursive tree. Now you might be interested, where is the problem over here? So here the problem is we solve these subproblems multiple times. So if you look at this recursive tree very carefully, you see that we are calculating Fibonacci for 4 2 times, and we are calculating Fibonacci for 3 times, and for others it's also multiple times. So the same problem have been calculated many times, and this is very time consuming operation. So what we can do over here is, when we calculate the value of, for example, Fibonacci 4, we can reuse the solution for other cases over here. So in this case, if we calculate the value of Fibonacci 4, we can use the value over here. That's why I made the repetitive cases as red. So we can use over here without calculating these cases over here. So when we do this, the recursion trees over here will not be required. So our recursion tree will become like this. So this is exactly the dynamic programming is meant for. So by saving the results of recursive calls, we can increase the efficiency of algorithm, and we can modify our previous algorithm like this. So if we put if condition over here, we can modify our algorithm like this. Now in this case, time complexity will become ON. So as you see in this algorithm, first we are checking that if we have calculated this Fibonacci series before or not. So if we have calculated it, we are taking from the array over here. If we are not calculated, we are inserting to this array over here. Now after modifying this algorithm, let's see how the recursion tree will look like. Now if you look at this recursion tree over here, previously these recursions were red because we were doing computation multiple times. Now since we are using the values from the previous call, so these calls are not required over here. So as you can see, the entire tree has reduced drastically, and this improves the time and space complexity. So by calculating the values of Fibonacci 4 and Fibonacci 3 over here, we will just use these values over here. So we don't need to go to the rest of tree over here. So this improves the time complexity of this algorithm. Now as we explained in the previous slide, we are storing the values of the calculated Fibonacci series in the array. So let's look at how the array gets filled in each step. So the temporary array will look like this. So in the first case, we know that first and second numbers are 0 and 1. Now in the case of top down, we are coming down from the main problem to the subproblems. So our problem is to find the Fibonacci 6. So we know that to calculate the Fibonacci 6, we need to calculate Fibonacci 4 and Fibonacci 5. Then by summing up, we can get the Fibonacci 6 over here. So in the first step, we will divide the problems into Fibonacci 4 and Fibonacci 5. Now in the second step, we need to find out the Fibonacci 5. Now we know that to calculate the Fibonacci 5, we need to calculate Fibonacci 3 and Fibonacci 4. So in this step, we will divide the Fibonacci 5 into two subproblems, which are Fibonacci 3 and Fibonacci 4. Now in the next step, we need to calculate Fibonacci 4. So we know that in calculation of Fibonacci 4, we need to get the values of Fibonacci 3 and Fibonacci 2. So that's why the equation comes over here. Now in the next case, we need to calculate Fibonacci 3. Now the Fibonacci 3's formula is like this: Fibonacci 1 plus Fibonacci 2. Now we know that first two numbers of Fibonacci is 0 and 1. So based on this formula, we can calculate Fibonacci 3. Now if we calculate the Fibonacci 3, we know that 0 plus 1 is 1. So we are storing this value. So we don't need to recalculate it in the next stage. So in the next step, we need to find out Fibonacci 2 and Fibonacci 3. So in this case, we are not calculating it because we have already stored these values. So by adding these values over here, we are getting Fibonacci 4. Now in the next steps, you see that we need Fibonacci 4 for Fibonacci 5 and Fibonacci 6. So we have saved the result, so we don't need to calculate it again. So based on this formula, we are just taking the values from here, Fibonacci 3 and Fibonacci 4, and calculating Fibonacci 5. And similarly, we are doing same steps for Fibonacci 6. We are not calculating Fibonacci 4 and 5. We are just taking the values that we saved over here. Now, as you see, in this case, we have started from the big problem and we have divided this problem into subproblems. So we are going from top to down. And after reaching to the smallest problem, we are calculating the value of this smallest problem. And when we calculate the value of this smallest problem, we are saving it in the array. So in the future, if we encounter with the same problem, we are just using the value from this array over here. So this is how the temporary array gets filled. And it always starts from the last and goes until the first, and then slowly starts building the solution coming back to the last. Now this is the reason this approach is called top-down method. So as you see, here we break the problem from the top and we go until the down. When we reach the down, we start solving the problem and go up. Now hopefully you have understood how we are using dynamic programming to avoid the problem that comes with the divide and conquer approach. So by using top-down method of dynamic programming, we can easily increase the efficiency of some divide and conquer approach problems. Now based on this logic, let's create Fibonacci series using memoization. Now here, we are going to create a method which calculates the Fibonacci series using memoization. So in this case, for memoization, we are going to use hashmap. So here, I'm going to declare our method inside this main class over here. So it's going to be like this: public static int. So I'm going to name the method fibmemo, and this method will take two parameters. The first parameter will be n. This is the number that we want to find the Fibonacci series, and the second parameter will be hashmap. So this will be the hashmap type of integer and integer. So it's going to be integer and integer, in which we are going to save our calculated subproblems over here. So I'm going to name this parameter memo. Then we are going to put our base conditions over here. So we know that in case of Fibonacci series, if n is equal to 1, in this case we are returning 0. If n equal to 2, in this case we are returning 1. So I'm going to write base conditions like this: if n is equal to 1, in this case I'm going to return 0. And if n is equal to 2, in this case I'm going to return 1. Then we are going to check that if calculated n is inside this hash map, in this case we are not going to do anything. Otherwise, if it is not in this hash map over here, in this case we are going to insert calculated value to this hash map over here. So it's going to be like this: if not memo.contains key, we are going to check n. If it is not in this hash map over here, in this case we are going to put it into this hash map over here with calculated value. So it's going to be like this: memo put. So we are going to insert with the key of n, and we are going to calculate value using Fibonacci formula over here. So it's going to be like this: fibmemo n-1 with the memo. So we are going to put same hash map over here plus fibmemo with n-2, and as a hash map will be memo over here. Now with this, we have successfully implemented our memoization over here. Then at the end, we are going to return the value from this hash map over here. So it's going to be like this: memo.get with the key of m over here. Now with this, we have successfully implemented Fibonacci series using memoization over here. So this means that if we have calculated any subproblem over here, we are going to save it in the hash map over here, and in the next time if we face the same subproblem, we are not going to call this function recursively over here. So this prevents extra cost over here. Now let's see how this is working. So here inside main method, I'm going to create new hash map with the type of integer, and I'm going to name it memo is equal to new hash map. Then I'm going to call this function for the Fibonacci series of 6. We know that the sixth value in the Fibonacci series is 5. So let's see how this is working. So I'm just going to print out the result to the console. So it's going to be like this: fib memo with n is equal to 6, and as the second parameter, I'm going to pass this hash map that we created over here. So let's run our code. Now you see that it's printed out to the console 5. So this means that our method works correct. Now with this, we have successfully implemented a method which calculates Fibonacci series for a given number and using memoization approach. So hopefully everything is clear about this implementation. So see you in the next lecture.